My name is Mark, and I'm glad to see you here. And we are going to dive now a little bit deeper in what happens under the hood of your application and what happens inside the drivers and how that affects your application when you're using reactive programming. That's not going to be an introductory session. That's a more advanced topic. And I'm going to cover modules for MongoDB, Redis, Cassandra, and Couchbase. As you have learned, there is no support for JPA. The reason is quite simple for that. JDBC is a fully blocking API. We do not want to create false expectations, and we do not want to move the actual problem that comes with blocking access in non-blocking scenarios, which means spinning up a thread pool and putting it just somewhere. We don't want to move the problem from one end to the other. That would just imply that we would have had found a solution for that, which we obviously don't, because we can't make blocking APIs magically asynchronous. That's the reason why there is no support. However, if you attended the previous Spring Data session, you maybe have heard that we are working on a Spring Data JDBC module. And SQL is something which has a very huge importance. We have also learned today from the keynote that the majority of users who are building applications with Spring Boot are mostly integrating with JPA. So that's a relational database for us. So most users are using relational databases for a very good reason, because SQL has its power, it has its strength, and not doing anything on that end would be something which we couldn't just let go. So that also was recognized by the Oracle people, by the JDK people, and they started addressing that issue lately at Java 1, where they proposed an asynchronous database access API, and in short, ADBA. This QR code will take you to the mailing list, and from there on you will find all the links to the existing proposal, to the code, to the whole discussion. And the reason why I'm telling you about that is in combination with Spring Data JDBC, we are able to pick up on that loose end once we have an API within the JDK, and secondly, once we have a reactive, well, in that case, not really a reactive driver, but an asynchronous driver available. And then we are able to bring everything what JDBC template brings us today in the imperative world to an asynchronous JDBC template by using features, by using asynchronous and non-blocking access to relational databases, which brings us a huge leap forward. I also expect other tools like Hibernate and maybe even Eclipse Link to come up with some integration at some point. But since we have everything then what we need with the asynchronous database access API, we can give it a try and see how far we come. One thing I mentioned right now is that asynchronous database access isn't reactive. The reason for that is the JDK team has its goal to make that API usable with the pure JDK tooling. It will contain an adoption of the Flow API, which is basically the copy of the reactive stream spec into the JDK. But there are no reactive libraries, no operators within the JDK available, which makes it a little bit hard to use just the Flow API if you're an application developer. So that means, in the end, that this asynchronous database access API will be based on completion stage, complete with future, and all these kinds of things. And that fits quite nicely. But it won't be fully reactive, but it will be at least a way to go and how to address relational databases. There's also another side to relational databases. You know, reactive programming for Spring is pretty much about resource efficiency. we are solving all the logs within the application. We are revamping how we react to the availability and processability of resources. But with relational databases, they follow inherently the asset notion, which requires transaction. And when you have concurrency within the database, one is writing, the other one is reading, then you synchronize at database level. That's one thing. And the other thing is you can't easily add more servers, more database servers to an existing relational database without really having a pain. Galera isn't fun only. Oracle RAC comes at a cost. DB2 comes at a cost, and you can scale to some point, but not really easily beyond that compared to NoSQL databases like MongoDB or Cassandra, where you just add commodity servers and then you basically increased your capacity. That said, let's dig into what reactive drivers and synchronous database access currently looks like to compare these both. For that, I prepared a few slides. This gray bar there is the transport over time, so that's the I/O. And what happens today with synchronous database access? Well, my application is requesting data from the data store. The data store starts doing things. In the meantime, I'm burning CPU cycles. So that's the thing we are solving with reactive database access. But compared to synchronous database access, we are burning cycles. We're waiting until the database sends us an answer. Once a response comes in, we are able to process that in the app, and then it goes so forth and so on. I think you get the idea about that. So in these holes where all the cycles were burned, we can improve with reactive database data access, because the threads aren't exclusively used in reactive data access for the whole time we are doing the actual database request, but rather we send a request to the data store, and as soon as the data store starts answering, we are able to emit those items through the reactive stream, through the publisher, and stream the data to our application as it is received. We no longer have to wait until the whole chunk is processed, and we no longer have to wait until the whole thread is blocked, because we do not block threads, you know. And because of smart prefetching, because of back pressure, the database driver always knows how much demand we have, where we are, and how many data it emitted. So the publishers, which are the connectors to our database, can now derive from the remaining demand whether the database driver should prefetch proactively data, or whether they should not prefetch. So if you have a demand of, say, 100 records, you already consumed 50, and the cursor from the database is exhausted, then the reactive driver knows, okay, there's still 50 remaining, and I can go again to the database and fetch the other one, while I am processing the remaining data I already received. And this is a huge improvement, because I'm reducing the gap between the data store access. Well, I keep my database more busy, that's one effect. But also, on the other hand, I keep my application more busy with useful stuff. I no longer burn these cycles, and things start to merge more nearly to each other. And I'm reducing lag and latency until the first element received, first element processed, and the latency between database accesses, and that makes it everything more tight. So everybody's happy then, quite. However, switching from imperative to reactive database access comes with some properties. Maybe you have learned already that reactive programming comes at a cost of learning the reactive framework, learning how to debug things. But more than that, it requires a threading infrastructure from your driver. So you are no longer providing a container thread like we did in a servlet or something like that, but we are requesting data from a driver, and the driver needs to provide the threading infrastructure because the driver is calling us. They are playing Hollywood. Don't call us, we call you, and they call us back again once data is available. So that's the one thing. The second thing is, the second most obvious thing is timeouts work differently. See, today, when we work with an input stream or a socket input stream, then we have two timeouts on it. The first one is a connect timeout. The second one is a read timeout. The connect timeout still applies in a reactive world because we want to protect our application if the remote server is down, so it comes back quite early. But there is no read timeout anymore. The reason for that is to know why there is a read timeout on an imperative API. The read timeout on the imperative API is to protect our application from a read that never comes back. So usually you don't read one single request with a single read, but you keep reading from the I/O until the protocol signals you completion from the server side. So when the server signals, okay, this package, this chunk, this cursor is complete, then you stop reading. But until then, you keep reading in a for loop or a while loop or something like that. And to protect your application to not come back ever, we have this read timeout. In a reactive world, the driver keeps reading without blocking anything. So it uses NIO channels, which are non-blocking by default. And when the read has nothing read, it just keeps coming back. So we don't have that timeout anymore. And we don't have that protection anymore. So therefore, our drivers need to come up with different timeout schemes. For instance, the command timeout, which means the command needs to be completed within this particular duration. Before that, we had the read timeout, which means, okay, if there was no data for, say, 1 minute or 30 seconds, then throw an exception. And now we need to shift that perspective from that very read timeout to until command completion. And that's quite a big shift because nobody really says that I could apply this previous 30 seconds or so to the whole command. Maybe the database is busy and it doesn't answer within that specific time with the command completion. So I have to rethink my timeouts again. Let's take a look on the reactive drivers, what we have there and what expects us there. Reactive drivers need to be end-to-end non-blocking. We have that already within JDBC. They need to process requests asynchronously so that I'm writing requests out to my driver. The driver does some magic and comes back with a callback, usually in the form of a publisher, but also a driver which is asynchronous is fine too. Well, we can work with futures. We will do that for asynchronous database access anyways. There is, however, one downside to that. If we adopt futures, we have to wait until all of the data has arrived and is decoded on the client side. A more reactive approach would be streaming in the data, decoding on the go, and emitting items as it's streamed, as is read. The big advantage is here we do not need to read all the packages which are sent from the server, but we can emit and work on really smaller chunks. And this, again, improves the time to latency, the time to the first emitted event. There are, however, a couple of other aspects like pooling and connection. So drivers need to use non-blocking pooling and non-blocking connects. That's not true for every driver. For instance, the Redis driver I'm maintaining, so yeah, actually that's a pity, is still using a blocking connection pool, so I got to fix that. To not create a blocking piece of code within the application. If you create a blocking request within the application, you run always in the harm that this blocking piece is so blocking that suddenly nothing happens. So a single synchronization, a single blocking call within your request line is able to happen to defunct your whole application. The reason for that is to understand how threading works. Well, maybe when you are familiar with Netty, you might know Netty uses event loops. So that's a loop, so that's a thread which runs in a loop and processes tasks. And what happens in there is when you get called back on a netty thread, it processes a task which was put in a queue and does its job. It's some sort of callback which ends up in my publisher. When I then start another database request, which is perfectly fine, it gets in-queued to the very same queue, to the very same thread. And if I do block in that very same moment, I'm preventing that thread from progressing and from actually working on that next task. So that's the reason why things start then to block and to never come back. So there's, however, a harm. If you do not block, you make sure that your application runs healthy. And keep in mind, every time you call block, a kitten dies, and we do not want a kitten to die. So what happens really inside the driver? To give you more understanding what happens under the hood. Well, you have a request and response from the perspective of your application. The driver is currently a black box, but let me fill it for you with meaningful things. So usually in a NoSQL world, you have multiple servers, so the driver has to select the most appropriate server. For MongoDB, it could be reading from slaves or masters, but however, the driver has to do that. It has to know about the topology and select the right server to go to. It needs to maintain a queue. You could have multiple concurrent requests, and you, depending on the server, you write only one request at a time. It's encoded to the transport, sent to the database server, and that's it. Then the database server starts acting, and as soon as a response comes back from the server, then the database stack is reactivated again. Under that, so when the write is done, then usually the request and the control comes back to your program. So that's the non-blocking piece here. And once the database sends you an answer, it emits an event, well, a netty event, that's something was read. And then it starts decoding the response. Depending on the chunk size and the number of bytes you have received, it's perhaps even able to decode a full element and start emitting that. If there is, however, no demand from your subscriber side, because your database server is not really aware that you are using reactive programming, the driver needs to buffer all the details. There are drivers who suspend from the client side the read, so which means that all the read buffers stay outside of your JVM on the OS buffers, which is pretty neat because you don't overwhelm your JVM if your JVM is quite slow, but your database is fast. So you shift responsibility where it really belongs to, and it's able to stay outside. WebFlux has a pretty similar feature. If there is no demand, it suspends reading from Undertow, Netty, and the other integration what we have. And then once the request completes, we get a termination signal to the subscriber propagated, and in the meantime, all the elements are emitted. So let's take a look on the first driver we have here. It's MongoDB. It's a reactive over asynchronous driver. So MongoDB provides two drivers, one RxJava one reactive streams one. Both are built on top of the asynchronous driver, which deals with callbacks. It's perfectly fine. The query cursor lifecycle is bound to my subscription. So if I terminate the subscription and say cancel, the cursor is killed. Otherwise, it's living until the termination signal comes in. It has a pluggable I/O, which means you can use plain asynchronous socket channels. And if you want, you can also use Netty. And if you want to use SSL, you have to use Netty because there's no SSL implemented with the asynchronous channels the MongoDB people did. So how does it work on a transport? You issue a query, the request is written to the transport, you receive a chunk. Because that's an async driver, which requires completion, it has to receive and wait until the very last chunk. And then the driver starts prefetching the next, God bless you, the next chunk, so that you have already the data available when you come there. And then finally it starts emitting events. So you see quite a lot of stuff that has to happen until you really get to the results. But it sounds sounds more scary than it actually is. One thing that's quite interesting is MongoDB has a batch size for cursors. How is this derived? Well, they did a smart move. They used the demand from the back pressure to calculate how many events to request. And to see how that works, let's take a look on the code. I brought a little bit of code with me. Links to the code are available at the ends of the slides. So let's see what happens here. I have very simple request that goes through a collection and finds all elements. And I have some logic in here, which says, let me zoom in there, which says, okay, I'm fetching elements from a MongoDB collection, so that's a log from my test. And what happens in the MongoDB listener, so that's the actual document, the actual BSON sent to MongoDB is find command with batch size of int max. So the reason for that is that MongoDB uses only integers for batch size. And then I'm basically all the data. Nothing really fancy, and it really works quite straightforward. However, if I start using operators like filter, that's what I can do, things may change. And also, if I start changing the demand, so what I'm doing here is I'm requesting 10 items, expecting the 10, requesting another 10, and expecting 10 to come in. Let's look how this, take a look how this looks on the wire. It is requesting the first 10 elements, so propagating properly my demand, then calling a get more function on a cursor with a batch size of 10, so again 10. And because I'm canceling here, the driver kills the cursor, so works everything like expected. So that's my way how I can achieve batching in here by controlling the demand, by saying how much elements I want to receive. And this correlates also with the number of requests I'm going to issue with MongoDB. However, there is a caveat to that. This is pretty much the same code like above, but with the difference that I'm using a filter operator. And let's see how this behaves. I'm requesting again 10, and I'm filtering on the name length of my elements. And what we can see here already is I'm getting a lot more log. So what happens here? So I'm requesting 10 items, and that's again the 10 items. But I'm seeing a lot of get more requests in here. How come? What's happening here? And if I take a look on the batch size, it's the batch size start go crazy. Thing is, the filter operator, where are we here? The filter operator is dropping elements. So every element that has that does not match the predicate I have is dropped, and then to keep up the demand, the original demand, the filter operator requests one additional more element from the driver. So the driver eventually uses up its buffer and sees, okay, well, there is still demand. Let's go back to the database. I have this here, my demand, and let's request more data. And the more I do that, the more requests I end up with, and the more latency I introduce back in. Stop, wait, that's nothing. I really want to do that. How can I fix it? Well, there is a possibility. You either write your own subscriber or put your own operator in between to make sure that the batch size is working. Or you go to the MongoDB tracker, issue tracker, and raise their ticket because, well, we do not like so many requests. Or we use Project Reactive to the rescue, which allows us to add another operator in between, which is the limit rate operator. And what limit rate does, basically, is it's a smart prefetching and limiting operator that says, okay, do not request more than n items from the database. And on the other hand, if the demand drops, because I have satisfied it to some level, it goes back again to the publisher and starts requesting more data. So that does smart prefetching for you. And if I run this test again, then we see we are receiving a request of 10, so that's the initial size I requested. And the number of get mores reduced, and the batch size isn't exactly 20 because the operator does some bit shift operations in there to figure out the best number of items to request from the database. But it's at least less requests than I intended to have. And if I change that to, say, 60 or something like that, then we will see that the number of database requests actually drops. And that's something you don't really see on the very first side, but that's something you will figure out over time, and you do not really want to figure out that in production, so probably that's the reason why you're already here. And you should really pay attention what happens with your driver when you start querying your database. How does it really behave? But the one thing I can promise you, it will behave differently, and you should have paid attention to that to not run into surprises. So we have that. Let's see what we have next. So we have that. With MongoDB 3.6, we get another feature provided, which is change streams. So if you have attended the previous session with Reactive Database Access, you maybe have seen tailable cursors. Change streams are something like events that tell you about document changes, and it makes a lot of sense to model those as well in a reactive way because you get notified about changes in your database. The next is Redis on my list. So for Redis, there is only one reactive driver. There are, however, other projects which are asynchronous nature, but these drivers are not really drivers, they are fully sophisticated clients. That's the reason why we did not integrate with them in Spring Data in the first place. Redis is based on Netty and Project Reactor, so it exposes mono and fluxes. Works perfectly fine on a single connection. So you do not have to spin up multiple connections within your applications. Redis itself is single-threaded, and adding more connections just adds more overhead, and there's actually no reason for that. If you go for Redis cluster, that's maybe a different thing, but still, Redis is blazing fast, and you can choose whether you go for a single connection or pool connection scheme. And the Redis driver works a little bit different than the MongoDB driver. So first, it's a reactive driver, which allows us to not only request data asynchronously, but to stream in data as it comes in. So this means when we receive protocol packages from the Redis server, we are able to read and decode the data on the fly and emit all the data directly to your subscription, which allows us to, again, reduce the latency until the data is processed. We do that until the full command completes. And if the demand drops, so that we have sufficient data, we no longer read from the I/O until the subscriber either cancels the subscription or signals more demand. And this is a really nice thing. And there you see, again, the difference between an asynchronous driver and a reactive driver, how they compare to each other. There's one specialty. Maybe when you're using Redis, you know that there is a case of a key not being present and being absent. In the imperative world, we would return a null value. Because null values are prohibited in reactive streams, we simply do not emit elements. That's again a change in terms of reactive versus imperative. It affects you especially in the case where you have multi-key commands where you access more elements. There you have then to pay attention to these particular bits. And I think I'm running out of time, and I think if you want to stay with me 2 more seconds, 2 more minutes, I will give you a short overview over Cassandra. Cassandra as well has no reactive driver. It provides an only asynchronous driver. That's a data stacks driver. And what we did from the Spring side is we wrapped it, provided a facade around of that, and exposed the Cassandra session, which carries the synchronous and asynchronous methods on it, in a reactive Cassandra session. Whoop. Yeah, where do we go? Oh boy, what a reactive session. I just type it right. So the reactive session is a facade, a bridge over the asynchronous session, and allows us to expose similar methods like the synchronous and asynchronous execute methods through a mono and a reactive result set. If you are interested in using that on a low level, so having all the control yourself, you can do so. Cassandra will come up with asynchronous reactive, more reactive driver in the future. That's already in the works, but don't expect it to happen this year or in the beginning of next year. So this will take quite a while. And since time's already up, I want to present you the resources where you can find all the code, all the slides. Just follow that QR code, then you will get all the links, all the good stuff to read. And if you have any further questions, I will be around here at SpringOne for a couple of more days. Thanks for attending my talk, and have a great SpringOne.